Hello, physics classmates and wandering YouTubers. Well, really lost YouTubers is more like it. My name is Not Important. This is the fifth and final lab, hopefully final. And for this one, I'm doing oscillation again because I love oscillation. That one is a lot of fun. So for this oscillation project, I'm using a weight, 8 pounds, which I'm going to convert into kilograms, a spring, which came off of a exercise stretching device, which I really don't know anymore, which is old and stuff like that. So I used that anyway, and tied it to a tree and pulled it back and let it go. And here we go. And here's my tracker program. Let me run it for you. As you can see, it's a beautiful fall day, and I decided to do it outside. And as you can see by the graph on the side, the weight is doing sort of an arcing motion. I know it looks crazy. I mean, it's very hard to track the weight since it sort of blurs. As you can see, it's very hard to pinpoint its location. But also, since the weight is sort of gyrating, as you can see right here, watch, see? It makes it very unpredictable and also causes its own force. And since I'm not capable of modeling the weight's own rotational force and a bunch of other forces that are acting upon it as it sort of swings side to side, it will make it very unpredictable. And as you can see later on, when I compare this in the Python model, it makes quite a big difference. There is also some slack in the system. The weight is sort of tied towards the end than it is in the middle. And also, if it were in the middle, it would probably be worse since the weight would be flipping around even more. And also, up near where the tree, where the spring is tied to, there is a bit of slack, and I couldn't really tie it any tighter. The rope sort of stretched over time. And here's a one-to-one scale that I will show you later compared to the Python program.
One of the most crucial equations for the fourth lab is figuring out t, the period of oscillation, but that one's very simple. So the more complex way of doing it is t equals 4 pi squared times the square root of m divided by k, m being the mass of the object in oscillation, and k being the stiffness of the spring. But since t is very easy to find, and k is what we were really trying to solve, we switch them around. And the new equation is k equals 4 pi squared, sorry about the typo, that's supposed to be 2 stars, times the mass time divided by t being the period of oscillation. So now once I find my inputs, being the mass of the object being 0.402 kilograms in scientific notation, t simply being the time it takes for or the top peak of the oscillation to go to the next peak of oscillation, or the lowest point of the oscillation to the next lowest point of the oscillation. And for this one is 1.71 seconds. So once you divide 0.402 kilograms by 1.71 seconds, then multiply it by 4 pi squared to the second 4 pi squared, you get K, the spring stiffness, being 6.9104. I believe this will vary because different students will have different feedback from tracker because of human error. So this is what I got. The next crucial equation is trying to figure out the spring's relaxed length. For this one, we need to figure out the spring's equilibrium, but that was already given by the video lecture, the first lesson of rope physics, and that being the length of the spring in equilibrium with weight at the end. With 0.402 kilograms in the spring, and its spring stiffness being K, being 6.9104, the spring's length in equilibrium is 0.7 meters. Now, the equation to figure out the relaxed length is we're trying to solve for LO, being your relaxed length of the spring. The equation is LO, relaxed length of the spring, is equal to the length of the spring in equilibrium minus the mass of the object times the gravitational force divided by K, the spring stiffness. After inputting my variables being 0.7 meters for the spring length, the mass of the object, the gravitational force being 9.8 meters per second, divided by the K, the spring stiffness, we get the result of being 1.2990, or being the identical length. We get the result to be LO is equal to 1.299 meters.
And here's my Python program. I've taken this from week 4, well, lab 4, and converted it to suit my needs. So here we go. We first to change the ball's mass, then input the ball's originating position, which is exactly the same from the video. Then input my CSV file, and moving on down, change the KS to suit which the spring really was, which I've verified my math multiple times to make sure it was such a large number, and also the relaxed length, which I just simply measured the spring. And also could have did it the more complex way by using the mathematical formula just for the heck of it. Now let's run the Python program. Right from the start, the ball's oscillation is completely different than the weight's oscillation in real life. The reason I believe this is completely different is because the weight is actually gyrating and creating its own force, which completely throws it out of whack what should happen in a controlled environment. Also, as you can see, it's a lot more predictable than what happened in real life because the string was sort of jumping up and down, the weight was creating more force in one spot than another, and therefore Fnet is sort of varying. My what if question is, what if the weight was dropped from up above and at an angle? Would that change the oscillation? And what if the weight and springing was changed? For example, what if this was done in space with a very, very light and stretchy spring?